Hello, everyone. Thank you for coming to my talk. I'm Chao. I'm actually a local Shanghainese here. I work for Google from in the Sunnyvale office in Google. I'm a software engineer, and I've been working on Kubernetes for more than 4 years. And this is my second KubeCon talk. Again, thank you for coming to my talk. I'm going to talk about storage migrator today. But before we go into today's agenda, I want to first share with you a story of mine. It was the first year when I joined Google. I was freshly graduated from graduate school, and it was my first on-call shift. And it's late in the night. My pager suddenly rang. Customer's cluster was crash looping. So I was a little nervous, but I just proceed with the procedure. I opened my laptop. I logged into my account, looked into the API server's log. I easily found the culprit in the log. The culprit, the error message is there's no job API, there's no job kind registered in extensions v1 beta 1 API version. I think this error message is a little vague, but it gives me some clue. So I looked into the code a little more. I found out that jobs is not available in this API version anymore. Jobs has graduated. So I think my next step is either try to fix the objects or try to delete the object. I got into contact with the customer. The customer told me those jobs are just deprecated objects. I have their permission to really delete all those jobs. I was very happy. I thought, that's it. All I need to do is just run a kubectl delete command to delete all those jobs, because they are the culprits of crash looping API servers. But when I tried to do the kubectl delete, I found out that the API server cannot handle the delete operation either. The reason is the jobs is not, the API server just doesn't recognize the jobs because they are in a stale version. The API server cannot interpret the object anymore. So I cannot do any operation on them. So my last resort, I really want to use it, but I had to, is to directly talk to SCD. This really wasn't the situation I want to be in, right? It's my first year at Google. I don't want to deal with SCD API because I've never touched those API. All I know is Kubernetes API. Also, I don't want to accidentally delete a customer's other data. So I was really nervous, but what can I do? That's my only option. API server cannot do anything at this point. So I had to spend like half an hour search SCD control, their client document, and try to assemble the command to delete those stale jobs. And I had to experiment it on my local environment to make sure those command actually works. After half an hour, I got the job done. I'm smart, but that's really not a situation I want to be in, and I don't want any of you to be in this kind of situation either. That's why I come to work on the storage migrator, and that's why I want to share with you how to use the storage migrator, so that hopefully this never happens to you. Okay. So that's my story. And now let's go to the actual agenda. So first, I want to share with you some background knowledge of how Kubernetes stores API objects. I think this is necessary for me to talk about storage migrator. And I just like to talk about API machinery stuff. It's fun. Then after the background, I'll talk about how come we will ever have stale objects in SCD, and how come that bug happened to me. And at last, I'll talk about the solution, the storage migrator. So let's begin with the background, how Kubernetes stores objects in etcd. This will be a little long, actually. So if you have an running API server, and if you go to the root path of the API server, it will return you the discovery document, which will tell you all the API versions, all the APIs that supported. And as you can notice, for a specific API group, like batch, usually there will be multiple API versions available. And those API versions are the evolution path of the API. So for example, here we have the batch v1 beta 1, which was the pre-GA version of the batch APIs. And we also have the v1, which is GA version of the batch API. And we also have the v2 alpha 1, which is an experimental version of the batch API. Usually the difference between those different versions are very subtle. They might have different field names. They might have different validation rules or default values. And for those v2 alpha 1 API, because it's alpha, it might contain experimental APIs. And one thing to notice is all those APIs, no matter it's v1 or v1 beta 1, as long as you are talking to as long as the namespace and the name of the object is the same, then the URL actually lead to the same object. So what I mean is, if you visit all these three different URL paths, although they have different versions in the URL, but because their namespace, all the namespace here is default, and all the object name here is pi, they're actually referring to the same object in the backend, which is the job in the namespace default and with the name pi. So those versions are just different. You can think of them as alias. I'll first just state how the things are today, and then later I will explain why they are designed like this. So now let's look at these API paths dynamically. Let's see how things work when the API server is actually taking a request. So first, let's look at when the user is creating an object. So the user might choose to post their object to the v1 beta 1 jobs URL. And what happens is the user will just provide a job object at this URL path. And this object in the request must be encoded in the v1 beta 1 version. That's a requirement of the API server. Because the URL says, what I accept is the batch v1 beta 1 jobs. So you must, the user must encode the object in the v1 beta 1 version. Otherwise, the API server will reject the request. However, after the API server has processed the job and before it stores it into the backend, the etcd, the API server will actually convert the object from v1 beta 1 to the storage version, which is actually the batch v1. Storage version, so it will convert it to the storage version. It will change the encoding, and then it will store it into the backend, the etcd. So here, the storage version is an important concept we will mention a few times later in the talk as well. The storage version, so literally, it means literally, it's the version the API server will convert the object to before the API server can store it into etcd. And for built-in resources, the storage version, it's pre-configured. It's coded, it's hard-coded. So it's tied to the API server's version. So for example, if you use 1.19, where are we now? We are at 115, right? If you have a 115 Kubernetes API server, all those storage versions for different API resources are already hard-coded. And for the CRDs, the storage version are dynamically configurable. You can configure them via the CRD's spec. Okay, now let's go back to the main topic. So previously we talked about what happens when you create an object. Now let's look at what happens when you're reading an object. So the user can choose to get the object from a different URL path at a different version. So if you remember, we created it via the v1 beta 1 path. But now the user tries to get it from the v2 alpha 1 path. So what happens is the API server will read the data from the SED, which is encoded as v1. And it will convert it to the version the user requested. So it will here the get request is hitting batch v2 alpha 1. The API server will convert the object to v2 alpha 1 and then give it to the user. The API server here is like a version hub of all the versions. It will do all the translation for users. Right. So aforementioned are how things work today. And I want to give some insights on why things are designed like this. The first is, why does the API server have to support multiple versions of an API? That's because we want to make sure that's for the server and the client compatibility. That's to enable different lifecycle management to decouple the lifecycle of server from the lifecycle of client. Let's look at an example. So let's suppose the API server only supports one version at a time. And this API server is at version 1.x. And you have a client which is talking to the batch v1 beta 1 endpoint. And once you upgrade your API server to the next version, and suppose it only supports one version, and the batch API has graduated from v1 beta 1 to v1, then suddenly your clients will stop working. It will get all the 404 responses, right? Because the v1 beta 1 isn't available anymore. So that's why but as things work today, the API server will support multiple versions at the same time. Then you can upgrade your API server first, and your client will still keep working. So you can upgrade your client afterwards, before you do the next upgrade of API server. So that's why the API server has to support multiple versions. It's for the compatibility between the server and the clients. The second why does the API server have to convert objects to the storage version? Why can't the API server just store things as they are passed in by the clients? Like if the user again, let's look at an example. So the reason is it's for old server and new server compatibility, but I'll explain it with an example. So let's suppose the API server store the objects as it's passed in. And the user is creating the job via the v1 beta 1 endpoint. And let's say the API server doesn't do any conversion. It just stores it as batch v1 beta 1. But you will upgrade your API server sometime. And at some point, the v1 beta 1 will be removed from the API server. And at this time, if your user try to read the things from the API server, it's not going to work because the API server doesn't understand the v1 beta 1 anymore. On the other hand, if things are stored in the storage version, which usually is the most recent version available, most recent stable version available, then even if the v1 beta 1 version is deleted, because the object stored in SCD is in the storage version, then this object is still interpretable. Of course, for things to work, this relies on the Kubernetes upstream maintainers to pick the storage version carefully. So they need to pick the most stable version as the storage version for every release of Kubernetes. So to highlight what we just said, the important bit is you need to make sure your objects are encoded in the storage version. Then you can upgrade your API server. Otherwise, you might have stale objects that cannot be interpreted anymore. So previously is the background knowledge. And now let's look at how I ended up in that story. Why would there ever be stale objects in customers' clusters? So you might have already noticed there's a loophole in all the designs I've mentioned before. That is, if as a user, if you create an object at some point, let's say you create it when your API server is at v1.15, and everything is working as designed, the object is converted to the storage version, which is batch v1, and it is stored in etcd. However, suppose let's say you forgot about this job. You never touched the job anymore, and 1 year later, your API server has been upgraded multiple times to, let's say, 199. It's an imaginary version. But at this time, the batch API can already be at v8. No one understands, the API server doesn't understand the v1 anymore. So although everything works as designed, the object is stored as the storage version, but because you forgot about its existence, you never read-write it, you never update it, the job becomes stale. And at this point, this thing is not interpretable anymore. This is actually what happened back in the story. The users, the clients, they created those jobs, I think in 1.3. So at that time, the storage version of jobs is extensions v1 beta 1. And because they actually don't need those jobs, they are deprecated. They never delete those things or update those things. And when we upgraded API server to 1.5, extensions v1 beta 1 job is already removed. That's why the API server starts crash looping, starts complaining about those stale objects. So this can happen to any cluster. Luckily, here comes our savior, the storage migrator. I want to summarize the job of the storage migrator in one sentence. So it's just a control loop that makes sure all the persisted API objects in etcd are encoded in their respective storage version. So that when you upgrade your API server, those objects will still be readable. I want to first highlight the features of the storage migrator from the user's perspective. So it's some very nice feature of the storage migrator. First, it's deployable by the kubectl. All you need to do is to download some YAML files and deploy it in your. It supports the API the migrator uses is Kubernetes style. It's conformant to the generic Kubernetes API, so the learning curve will be very low. Also, this thing is fully automated. Once you deploy it, you don't need to worry about stale objects anymore. The migrator will do the job for you. Also, it's resilient to failures. Like if your API server crashes, if the migrator itself crashes, it will recover from the failure. Once it recovers from the failure, it will continue the migration job as as before. Also, it's vendor specific, so you can deploy it in any cluster, any environment you like. Let's look into some details. So this is how you can deploy the storage migrator in your cluster, all you need to do is to download the YAML files from the repository, which is completely open source. And then you just apply all the manifests, and it will just create the migrator, start the migrator in your cluster. And let's look at the migration API. So this is a sample migration. So I highlighted the important field. So let's first look at the spec.resource. So here it says batch jobs v1. What it means is this is a migration request for batch objects. So it requests the migrator to migrate all the jobs in your SCD to make sure they are in the latest storage version. And the name here is just a combination of the resource name and the group name. Next important bit is the continual token. So this is just a checkpoint of the migration progress. So this field is updated by the migrator automatically, so that even if the migrator crashes, and when it comes back, it will just continue from where it left. It will continue from this checkpoint. The next important bit is the conditions. So this is also a regular Kubernetes API, right? It says, so here the condition is it's running. It means the migration is still ongoing. And because this migration, thanks to this migration API to be fully Kubernetes conformant, you can use some very generic kubectl command to talk through the API. So for example, when you want to upgrade or downgrade your API server, you need to make sure all the migrations have completed. And you can do this with a one-liner using the kubectl wait. Because the migration API uses the conditions in their API. So you can just say kubectl wait for all the storage migration requests to be successful. All right, so now let's talk about, I want to dive into the migrators and tell you how it works internally. So that's, I want to demystify it, so when you ever have to debug it, it will be a little easier. So basically, the migrator is two loosely coupled controllers. On the left side of the graph is the migration trigger controller. It will just fetch the discovery document from the API server continuously, actually periodically. And it will detect when the storage version has changed. So for example, if your API server has upgraded to the next version, the storage version might change. So at this point, the trigger controller will detect the storage version changes. And it will post the migration requests once it detects the changes. And on the right side of the graph is the actual migrator controller. It just watches for all the migration requests. So once the trigger controller posts the migration requests, the migrator controller, it will actually migrate the resource for you. So for example, if the storage version of the job has changed after your server upgrade, the migration trigger controller will post a migration request. And the migrator controller, it will notice the new migration request and actually migrate all the jobs for you. Let's zoom into how the migrator controller actually migrates a resource. So here, the migrator controller is on the left. And we have API server and a CD and SCD on the right. So to actually migrate a resource, the migrator controller will first, it will use the chunking list API to list the first 500 objects of the resource. So in our example, it will just list the first 500 jobs. And then it will it get the name or the list of the names of the jobs. Then it will get the first job from the API server. And without making any change, without do any conversion, it will just write the job back into the API server. It actually, so the migrator controller itself is actually dumb. It doesn't know all those API versions. All it does is just read the object and then write it back to the API server. And the API server, once it receives the object, it will actually convert it to the storage version and write it to the CD. And if the object is already in the storage version, then the API server will not do anything. It will just return with a no op. So this is the actual migration, how the migration is done. It actually relies on the API server to do the conversion. And the migrator controller will do this thing 500 times until it finishes one chunk. After one chunk of the object is done, it will record the progress in the migration.spec. That's where the continual token comes from. So basically, it will say, I have already upgraded these 500 jobs. If I crash, it's a checkpoint. When I crash, when I come back, I will continue from this continual token. So the migrator controller will do this repeatedly until it has finished, until it has iterated through all the instances of this resource. Then it will mark the migration status as succeeded. So this is the life cycle of one migration request. So in your system, there might be multiple migration requests for different resources. They are just multiple instances running to migrate those resources. Yeah, that's how the migrator works. And at last, I want to talk about the timeline. This migrator itself is in the Kubernetes. It's hosted in the Kubernetes 6 repository. Currently, it's still alpha, but it has met all the beta requirements we listed in the CAP. So we plan to graduate it to beta in this month. And then we plan to make it a GA in Q3 of 2019. So at this point, I want your support. I hope you can try the migrator in your own cluster and report any issues you have found so that we can make it GA in the next quarter. Yep. That's it. Thank you. Have any questions?
What happens when you're doing the migration? There are added or deleted jobs in the list.
That's a very good question. The interesting thing is, I don't care about those newly created jobs. That's because after you start your migration, and if someone comes to create a new job, those new jobs they must be stored in the latest storage version, right? Because it's the latest API server handling the request. So all we actually need to migrate is the jobs that's created with the previous API server version. So I don't actually care about those things. And if you delete the job, of course, if it's gone, then the migrator will just because the migrator will just get it and then do a put, right? If it's deleted, then the put will fail. So migrator will just ignore it.
I think there is a potential issue. For example, when you have migrated 500 objects, and during the next batch, some objects are deleted. So when you're going to list the next 500 objects, maybe some objects are skipped because they are in the first 500.
Oh, sorry. So this continue token is not based on the index of the things. Right, so you're saying we already listed 500 things. We should start from the 501 thing. And because you deleted something, the 501 thing has actually become the 400 something. But that's not how the chunking API works. So all the chunking API is actually based on the name of the object. So when you say I listed the first 500 thing, and the last job name is say A, so then it will just when you send the continue token to the API server, it will just continue from the next thing in the alphabetical order. It's not based on the index of the things. It's not the number.
Okay, thank you.
This is very tricky.
I asked how fast it is, or give me some numbers on how fast it is on a small, medium, and large Kubernetes cluster.
So we did some math. If you are actually migrating things like config maps, let's say you have 1 million config maps, and suppose your QPS is like only 5, then it can take days.
And is this likely to have some influence on triggering API call limiting or anything because of what's going on with this tool?
Because we have the QPS limit, right? The client has a QPS limit. If we set it to 5 in default, so it shouldn't cause too much traffic on the API server.
Is there a way to filter this so that you only upgrade one namespace or some portion that you control?
No, but I don't see why that can be helpful, because even if you only upgrade one namespace and then you upgrade your API server, then things in other namespaces are still stale, right?
There's some backup and restore scenarios where there are things like the Valero project that back up Kubernetes not through in a full etcd backup, but through API calls, and then have a restore process. Now, it could be that since the recovery would be writing, they trigger an auto update anyway. But I was just wondering about that scenario.
So you're saying there are other processes that can actually trigger the migration?
Well, a Valero backup could back up an entire cluster through API calls. Then you could selectively restore just one namespace.
I see. Yeah, that could be.
But you're restoring to the API server, right?
Right.
So it goes back to Chao's original point.
Okay, effectively it's doing what this is just because you rewrote it. So you wouldn't even need to worry about it. Okay, thanks.
Let's answer one last question.
Let's take it short. If I am trying to migrate some workload that can generate child workload, like let's say deployment, and it generates replica set, and when I upgrade this deployment, is that means those replica set will immediately be destroyed?
No. So this migration, it doesn't change the semantics of your object. It doesn't change the spec of your object. It's a no-op, right? All it does is force the API server to rewrite the object in SED to the latest version.
So if I upgrade the API server and the deployment and the replica set, their storage version are both upgraded. All I need to do is first migrate the deployment and then migrate all the replica set. And that's it, right?
Yeah, that's true. But this is automated. The triggering controller, it will detect that the storage version of the deployment and the storage version of the replica set has changed. So it will post 2 migration requests for you.
Cool. Thanks.
All right, thank you.